Today, we're going to continue our look at definite integrals, and we're going to focus a little bit more today on antiderivatives. This is because yesterday, not only did we introduce the notation for the definite integral, where we say the integral from a to b of f of x dx, we also introduced the fundamental theorem of calculus, which brought up the concept of the antiderivative. Remember that the definite integral from a to b of f of x dx is going to tell us the area under the graph of f of x and above the interval from a to b on the x-axis. The fundamental theorem of calculus says we can get there by looking at the antiderivative at just the endpoints of the interval. Capital F at b minus capital F at a, where capital F is an antiderivative of f. That is, capital F prime is equal to f. So this introduces the concept of the antiderivative and also gives us this really cool conclusion where if we want to know the area under a function and above an interval, we just have to look at the antiderivative of the function at the endpoints of the interval. This concept of antiderivative is just like like you think it would be. All those rules for derivatives are now going to be rules for antiderivatives. So when we learned that the derivative with respect to x of x to the n was nx to the n minus 1, we look at the process of taking the derivative. We multiply by the exponents, and then we subtract 1 from the exponent. So the derivative of x to the 5th is 5x to the 4th. So what we're doing for a derivative is we multiply by the exponent, and then we subtract 1 from the exponent. Those are the two things that we did to find a derivative of a power function. Multiply by the exponent, then subtract 1 from the exponent. If we're going to be doing something called an antiderivative, we're probably going to be doing this process in reverse. So the antiderivative if I want the antiderivative of x to the n dx, where the derivative says multiply by the exponent, then subtract 1 from the exponent, for an antiderivative, I'm going to do the process in reverse. I'm going to first add 1 to the exponent, and then the inverse of multiply by the exponent is divide by the exponent. So an antiderivative of x to the n, to undo this derivative process, we add 1 to the exponent, and then we divide by the new exponent. So here is how we can find an antiderivative of the power function. So yesterday, that's what we did with this 3x when we found the antiderivative of 3x. We read the 3x as 3x to the first power. So if I want to calculate the integral from 1 to 4 of 3x dx, I'm reading the 3x as 3x to the first power. So my antiderivative is going to be 3 times x to the 1 plus 1, which is 2. And then we'll divide by the new exponent of 2. Since the derivative is a linear operator, it respects scalar multiplication and vector addition. The antiderivative is also going to be a linear operator. And so that 3 is just going to get carried along. It's a constant multiple, and we just carry our constant multiples along when we're doing derivatives. And so we'll carry our constant multiples along when we're doing antiderivatives. Now we find the antiderivative. This is capital F at x. So little f of x is 3x. So capital F of x is 3 over 2x squared. And the fundamental theorem of calculus says we evaluate the antiderivative at the endpoints and subtract. So the way we can note that we're going to do that is we'll put a vertical bar at the end of the function and say evaluate this from 1 to 4. That means plug in the 4 and then plug in the 1 and subtract. So I've got 16 times 3 is 48 over 2 minus 3 over 2. And so 48 minus 3 is 15 over 2. We should check to see that this matches what we think the definite integral should tell us. This should be the area under the graph of 3x and above the interval from 1 to 4. So if I look at the graph, the area under the graph of 3x and above the interval from 1 to 4, we're dealing with a trapezoid. So if we just find the area of that trapezoid, if we just find the area of this trapezoid, that should give us 15 over 2. So let's find out. So our trapezoid has one base of 3 and another base of 12 and a height of 3. So the area of a trapezoid is going to be the average of the bases multiplied by the height. I put 48 minus 3 and I came up with 15. It's because I only partially wrote the 4. 48 minus 3 isn't 15, it's 45. So I want the area of the trapezoid should be the average of the bases multiplied by the height. 12 and 3 is 15. 15 times 3 is 45. 45 divided by 2 is 45 over 2. So now there are two instances where the process matches our intuition about what should happen. Now let's change the function a little bit so that we don't have a formula that we can check. Now that we're 100% convinced that this process will absolutely deliver the results that we want, because we've seen 2 whole examples, let's now look at the area under a curve where we don't have a nice formula for it. Let's say, for example, I want to calculate the integral from 1 to 4 of just plain old x squared dx. This is going to tell us the area under the graph of x squared and above the interval from 1 to 4. Let's draw a picture of this, because we were trained in our algebra classes to always draw a picture. So I'm going to draw the graph of y equals x squared, which is going to be a parabola. I don't know why I drew so much parabola. And we're going to go from above 1, I'll just stop right here, to 4 on the x-axis. So at the area under the curve, x squared, and above the interval from 1 to 4 on the x-axis. So under this curve, and above the interval from 1 to 4 on the x-axis. Now, this is not a trapezoid, and we don't have a formula for a trapezoid where one of the non-parallel sides is a parabola. It's just too niche of an area that we need to find. Trapezoids, those are everywhere. But trapezoids in which one of the sides is a parabola, or one of the non-parallel sides is a parabola, that's just like not a thing. So, fortunately for our heroes, we have this definite integral technology and the fundamental theorem of calculus and antiderivatives. So if our little f of x, if our function that we're integrating is x squared, the exponent is 2, our antiderivative to get the antiderivative, we add 1 to the exponent, and then we divide by the new exponent. So our antiderivative is 1/3 x to the third. Now we can use the fundamental theorem of calculus. So the integral from 1 to 4 of x squared dx is going to be 1/3 x cubed evaluated from 1 to 4. So I plug in the 4, and I plug in the 1, and we subtract. So the 4 cubed is 64, 1 cubed is 1, So I get 63 over 3. We don't have a formula for this non-trapezoid like we did in the previous problem, or in the one before that where we had a triangle. Where we had a formula for a triangle, and so we could verify our result. So unfortunately, we don't have this very specific area of almost trapezoid, but one of the non-parallel sides is a parabola, and the other non-parallel side is perpendicular to the two parallel sides. That's just way too specific. If we start making a book for that, it's going to go on forever. Fortunately for our heroes, this was a numerical calculation. The answer was just a number. And that means we might be able to check it on our calculator. So that raises the question, hey, can my calculator verify this? And the answer is no. So I don't know why I even brought it up. I'm just kidding. Of course, the answer is yes. We've just got to ask the calculator nicely. Actually, we can be 100% rude to our calculator. It doesn't seem to care. Although I haven't tried being nice and then being rude to the calculator and see if it wears the battery down faster. Maybe next semester I'll have to give that a try. First, we need the integration command. So for that, we're going to need to press the math button, which is funny. It's a calculator. They're all math buttons, but press the one labeled math and scroll down to number 9, FNINT. So this is for numeric integral. I don't know why numeric derivative in number 8 is just n deriv, and number 9, the integral for numeric integral, is FNINT. But I imagine someone over at Texas Instruments does not like integration. So we are calculating an FN integral. The syntax for the numeric integral command is we start off with the function, integrate x squared. Oops. I am currently in parametric mode. Go back to function mode. There we go. So we calculate a numerical integral of x squared dx. To indicate the dx, we put a comma, and the next piece is x. So integrate x squared with respect to x, and then we put in the endpoints of the integral or interval separated by commas from 1 to 4, and then we hit close parentheses for good habits. Then we hit enter and hope that it comes out to the same thing I got previously. So your calculator has this command, and you can use that to check. We can use it to check the previous one. We can go math 9 and integrate the function 3x with respect to x from 1 to 4, close parentheses, because we're civilized, and hit enter. And there's the 22.5, the 45 over 2 that we got before. So what a cool thing that our calculator can do. So we need the FNINT command. Then we put in the function, and then comma x, and then comma 1, and then comma 4, and then we close parentheses because we are sophisticated and civilized, and we were not raised in a barn. I don't know if people say that anymore, but someone leaves a door open. Say, hey, were you raised in a barn? So the FNINT command is under the math button. So I put a box around math to indicate that's the button that you press. And then that first menu is the math menu. So press the math button, and in the menu up at the top, it says math, and you want to go down to 9. So then it's just math 9. Then the next thing we type in is the function. Then we put comma x. That's like us telling it x is the variable. So that can go in for the dx parts. And then from 1 to 4. And that's the syntax for the definite integral command on the TI calculator. Any questions?
Yes, Professor Rich, if you don't mind. On the previous example, so we can use both. We can use the antiderivative, and we can also use the area of the like 1.5, multiply the base and the height. Both of them we can use to get the area. On this one, since it's the trapezoid, that's why we use the antiderivative to get the area. Am I right?
On the previous one, we were able to use the formula for the area of a trapezoid because the figure was a trapezoid. On this one, the area is not actually a trapezoid. It's trapezoid-like, but it's not a trapezoid, so there's no formula for the area. We have to use the definite integral.
Yes, that's what I'm trying to say. We don't have a formula. Got it.
Correct.
Yes. Thanks, Professor Rich. Just one case, if we have a formula, then we can use both method. Am I right? Calculation.
Well, it depends on what you're being asked to do.
Oh, okay.
Any other questions? Great. Let's look at another example and see what it's going to tell us. Let's suppose we want to calculate the integral. Let's go from 0 to 2 of x squared minus 4 dx. Now, this is supposed to tell us the area under x squared minus 4 and above the interval from 0 to 2. However, we might notice something about this function. Let's take a look at what's going on. If we look at the graph of this function on the interval from 0 to 2, we notice that this graph is not above the x-axis. The graph of x squared minus 4 is a parabola. And between 0 and 2, having trouble with my parabola drawing today. Between 0 and 2, x squared minus 4 is below the x-axis. So here, we're not going to be finding the area. There's no area under the graph and above the interval. X squared minus 4 is below the x-axis. So it's going to be above, we're going to be looking for maybe, what we'll be looking for is area above the graph and under the integral. Because on the interval from 0 to 2, the function is negative. Let's see what the fundamental theorem of calculus has to say about this definite integral. In this case, our function f of x is x squared. We know the antiderivative of that, but we also have this minus 4. We know the antiderivative of x squared. We just did that. It's 1/3 x cubed. If we think about 4 as being 4x to the 0 power, we can add 1 to the exponents and divide by the new exponent. So our antiderivative is 1/3 x cubed minus 4x. And then we'll evaluate that function from 0 to 2. The other thing going on with this example is that we're finding the antiderivative of a function with 2 terms. And I just took a term at a time. So it works just like how we think it would work. So we evaluate the function at the endpoints. We get 1/3 times 2 squared. 2 squared is 4, so we get 4/3 minus 8 minus 0. This is all 0. And 4/3 minus 24/3 is going to be negative 20/3. If I grab our calculating machine and we math 9 this thing, we're integrating x squared minus 4 with respect to x from 0 to 2, close parentheses, and we get negative 20/3. Why didn't I get 20? Oh, I didn't cube things. I use red pen like I'm correcting it. It's not squared, it's cubed, so it's not 4. 2 cubed is 8. And 8 minus 16, or sorry, 8 minus 24 is negative 16. Yeah, minus 4 points to me. That means everybody else gets 4 points, but you all have to share. Even the students that aren't here. So it's negative 4 points divided by 50 students. So everybody gets plus 4/50ths of a point. Good thing we checked. So here's what we find when the function is below the x-axis. The definite integral, we'll just call that negative area. The definite integral reports area below the x-axis as negative. The definite integral calculates area below the x-axis as negative area. If I flip this function over to be negative x squared plus 4, so if I flip this function over, and trade on my x squared minus 4 for negative x squared plus 4, that puts the function above the x-axis, and now the definite integral is going to call that area positive. So if I said, what is the area bounded by the y-axis, the x-axis, and the graph of x squared minus 4, the area is 16/3. The definite integral from 0 to 2 of x squared minus 4 is negative 16/3. The negative indicates that the area is below the x-axis. Any questions? Incorrect. There is a question. What if we have a function that shows up below the x-axis and above the x-axis? What if we were looking at the graph of x squared minus 4 but not just on the interval, oops, but not just on the interval from 0 to 2, but the interval from 0 to 5. Now the graph is not just below or just above. What's the definite integral going to do with this area below and the area above? You could probably tell by the fact that I wrote this in I crammed this question into some corner of, not really a corner, but this open space, and I separated off with a box with not enough space to explain what's going on with these two areas, the area below and the area above. This is the question that I am not going to be answering today. And that's because y'all have a whole weekend to answer what's going on what's the definite integral going to do with this partially below and partially above the x-axis function? Any questions? So there's the question that I'm not going to answer today. And that's going to do it for today. That's going to do it for this week. Everybody have a nice weekend. I'll see y'all on Monday. And thanks for playing.